Okay, shall we start? Um, Before I do so, um, I recognize that originally we were planning of admitting something like 400 plus students, and there were quite a number of appeals, and so the department has opened up, has increased the enrollment for these two modules. As a result, the tutorials that we have catered for 10 groups are not quite enough. And because of the seating capacity of the seminar room, which is at the max is 60. So some of the tutorial groups have already reached that maximum. And so the department has opened up 4 more tutorials, and that would be tutorial 1, that would be Monday 1 to 2, and then tutorial 12, 4 to 5, and then the other 2 are Tuesday and Thursday 5 to 6. So if you haven't signed up for any of the tutorial, you can't do so online, but you have to do it manually with me. All right. So during the break time, please, if you haven't have any group yet, you are asked to come down here and then sign up. And if you have signed up for others, tutorial group 1 to 10, but you find that it might be better for you to change it to the new time slots, you can do so. We allow exiting from your current groups to one of the 4 groups here, because these 4, we still have quite a lot of places for signing up. But I won't, the other instructor and myself would not allow you to switch to 1 to 10 if you haven't done so, because we really reach our maximum capacity. Okay, is that all right? I think I'm speaking to many virtual students, who are probably watching our webcast sometimes. If you haven't signed up for tutorials and you are not here, what you can do is you just go to any of this, one of the 4 here, and you just tell the instructor or the tutor that you are signing up for this tutorial. So that would be fine. But if you go to T1 to T10, then you need approval from either myself or Professor Chan from the other lecture group. We want to maintain the seating capacity. Tutorial 2 and 3 already reach our max, so you may not even have a seat there. So this is pretty bad, right? All right. Okay, so so much for the announcement. And then I do not quite remember the date, but the midterm test has already been finalized. It will be on one of the, it's in the morning of a Saturday. I think it's either October, the Saturday before you are coming back after the break, something like that. It's something like October, early October. But I will put it in the information sheet as we get the confirmation. Okay, I think it should be October the 5th. And it is, I think sometime maybe 10:30 for an hour. All right. So I will give you more information, very definite information on Tuesday. Now, one of the reasons why we have it had in the weekend is something that neither myself or the other instructor would like to do so. We also don't want to come to the campus on Saturday. We share the same interest. But having about 500 some students, it is almost impossible to find a common time slot and then a place where we can have the tests all at the same time. So Saturday, actually we weren't even sure that we can do it Saturday. Okay, so we were given some priority. And so that's why we can choke the place, all right? So, okay, let me recap what we have done. Last lecture, we basically introduced you different approaches of probability. Some of the problems can be approached by more than one way, like the classical probability. And basically, the classical probability is assuming the outcomes are equally likely. And then we basically do careful counting. And that is why we have to introduce the two rules or two principles of counting, the multiplication principle and the addition principle. Counting can be very tricky, but it occurs very frequently, especially for computer science or engineering students, because very often you're dealing with discrete structures and you need to count them. And then there is another approach, is what we call a frequency approach, and it is gaining more and more prominence nowadays because the computer speed is just, fairly fast now. In a lot of situations where you can actually describe the underlying process of generating the random phenomena, then you can actually write programs to mimic the same process, but from which you can, but the computer is capable of doing it many repetitions. So basically, you are repeating the experiment over and over. And so you just look at the frequency of the event that you are interested, and then you have an estimate. Now, in the event that certain situations you can either do it this way or do it this way, the answer might differ a little bit, provided that, of course, you did it right in here. If you did it right, the answer would be, exact, all right, in that sense. Whereas your frequency approach would be subject to variations. Suppose you do it 1,000 times, you flip the coin, and classical probability tells us that the probability of having a head is half. But if you are doing it, say, 100 times, you do not expect yourself to get exactly 50. You will get 50 plus or minus something. And plus or minus something is the variations. When we get to binomial distributions, we'll be able to describe what kind of variations is to be expected. Okay, and it is usually of the order of square root n, whereas your average number would be order n. So when you try it many times, n would be much bigger than the square root n, meaning that your expected value and then the variation will be much smaller compared to your actual count. Now, so something that you have to be aware of, because when you are using a frequency interpretation, which is simulations, then you have to recognize that you have plus or minus something, all right? And of course, in order to be accurate, we have to spell out plus or minus what is that, all right? And when we come to binomial distribution or some other places, we'll talk about it. Personal probability, it really depends on the person, whether the personal probability is more reliable versus completely arbitrary. There are occasions that when you ask the medical doctor, when you are going through a surgery, he will say, a certain percentage, say 1%. The 1% might be from literature that he had read or from his own experience. But if it's a very rare kind of a surgery, of course you don't want to challenge him because especially he's the one who is operating on you. Suppose he say, oh, I have 67% success rate. But then he had, since this is a very rare surgery, he had only done it 3 times, and 2 times are accurate. So 67% plus or minus a very big percentage range. All right. So at least he has some experience to talk about. 67%. But if you ask some other situations like whether the market will crash, say in a month's time, the probability can be quite arbitrary, especially you ask someone who is not very knowledgeable about the situations. So why I'm emphasizing on this, because people do talk about probability in a very loose way, and you just have to be guarded whether the probability the person mentioned comes from very serious calculations or from frequency interpretation from his own experience or from literature, or basically he's just top of his head kind of a probability. Okay, so we talk about the 3 axioms of probability, basically only 3 assumptions, and that is very neat there. All right, so the first 2 are basically some normalization things, and then the first one is saying the probability that we assign can't be negative. Whether it is less than or equal to 1, if you take the proposition 2 that we have already proved, bigger event, bigger probability, and so the sample space is the biggest event possible. So, and since in axiom number 2, we assume that this is 1, so probability of A has to be less than or equal to the probability of S, and so this upper bound sort of is actually a consequence from these 3 axioms. So we don't even need to spell this out in my assumption, but it's no harm. So this is the main thing. The main thing that you have to watch out is they are mutually exclusive, meaning that if you draw them on a Venn diagram, the A1, A2, and so on are distinct, non-overlapping disks or on non-overlapping circles. Okay, if there is some overlap, you have to watch out. Okay, so I think we have done this, and so we talk about the principle of inclusion-exclusion. Basically, what we do is we include everyone one at a time. So the first line is I include individual event, and I add them up. But in the process of adding them up, I have counted the overlap. Okay, there are many patterns of overlap. I have counted the pairwise overlap more than exactly twice. Okay, here. And so I have to take them out. But when I take them out, I'm taking out a little bit too much. Taking out those that belongs to 3 of them at the same time. So that is why I have to add them back in. So this formula actually can be applied to not only 3 events, but in n events. But then the expressions, as you anticipate, would be sort of like n lines. The first line is individual probability, and then the second line would be the minus of the pairwise probability. and then the third line with all the triple event probability, and you have to add them. And then the next one would be minus all the quadruple events and so on and so forth. So, so you basically include everything in, but when you include it, you have double counting, and then you exclude, but when you exclude too much, so you have to put them back in, and so on and so forth. All right. Okay, so we have done this. All right. Now, the assumption fair coin or fair dice is important because if we do not have this, then we will not be able to say the probability of head and probability of a tail is equally likely, because the basic assumption of the coin being fair is that I have no preference as to whether it's heads or tails. I have no particular preference. So similarly, for a fair die, for a pair of fair dice, it would be any possible outcomes, I and j, as long as I is some number between 1 and 6, and then j is between 1 and 6. They are all equally likely, and so you have the same probability. I don't know whether you notice it in a lot of serious places where they, like casino and all this, they actually fill up the die with some white stuff there, because the die with 6, you have to carve out more from the die, whereas say if it is say 1, you carve out less. I don't know, I mean, but they put the 1 big, the dot is much bigger. But the whole idea is to make sure the die is equal, I mean, the weight is uniformly distributed, so as a result, the die is fair. It's not loaded. Okay. So these are the underlying assumptions when we are doing the equally likely outcomes. Now, of course, later on, there will be situations when we look at the Monty Hall problem, the equally likely outcomes in one of the arguments is flawed, all right? And so, and it's a good illustration of how equally likely assumption is being misapplied, all right, when we get to there. Okay, so I think we have done this. And so basically calculating the probability of the event that you are interested in, reduced to doing some counting the number of outcomes in A and counting the number of outcomes in S. And I think when I left the lecture in the last lecture, one way you can think of it is the probability and this. So there are 3 numbers that are involved. And so as long as you know 2 of them, you will know the others. There are some computer very difficult combinatoric problem people are interested is to prove that A is not empty. All right. So we, in a way, people want to prove that a certain algorithm or whatever will have a solution. All right. A solution corresponds to A here. And so because the algorithm is so difficult to analyze for general situations, people resort to proving the probability is positive. If the algorithm is random, I mean there is stochasticity in the algorithm. And so if you have this is positive, then it would force the numerator to be positive. And so they have this what we call non-constructive proof that a solution will exist, all right? So they are not able to produce a solution, but they are able to show in this probability argument that a solution exists, okay? The drawback is, of course, it is non-constructive. You know it exists, but you don't have a procedures to find it. Okay, I think we have done this. So to compute the probability of rolling a pair of fair dice, in order to get 7, will be like this. So I enumerate them, and there are 6 outcomes. So the entire collections of outcomes is 36 because it comes from 6 times 6. So I have 1 over 6. And I want you to calculate these probabilities. We have done one, the 7 here. And so I want you to do, the sum is 2. It is very easy. A sum of 2, it forces the pair of dice must be 1, 1, and no other choice. All right? So the probability will be 1 over 36. And so you will have this probability. If you really do the calculations, you will find that the probability increases as the sum increases, and then it will come down. All right? And having 1 over 6 is the largest. A lot of dice games or casino games has something to do with a pair of dice and depending on the sum. So, so you are not doing something just for these situations. We will revisit these situations when we come to conditional probability. Okay. And now another similar example that we like to do is this is what we call the urn and ball model. The urn is a generic thing because you can think of the urn as picking things from a population, from a nation, or from a location, or from a set of files or whatever. So we just have a generic and term urn here. Ball may not be really ball. I mean, it could be people, it could be some jobs or some descriptions. All right. So we are picking 3 balls from an urn, and the urn contains 6 white balls and 5 black balls. So what is the probability that one of the drawn balls is white and the other 2 are black? So this is the combination. 11 balls, I choose 3. So I will have 165 ways of drawing 3 balls. And so as a result, the number of such combinations is 165. And then to get 1 white, 2 black, you have to choose 1 white from the 6 whites, and then 2 blacks from the 5 blacks. So that would be this one. And so the probability will be just 60 out of 165, and it is 4 over 11. Now, of course, this is a reasonable assumption, but there is actually some hidden assumption which we in normal situations we won't consider it. We are thinking of the white balls and the black balls are about the same size, but I think I mentioned it. If some are soccer balls and some are marbles, when you are picking it, it's more likely to pick the bigger one. And so this is what we call size bias. Now, these things happen. Suppose you are observing an event within a window period, and you are looking at, say, for example, some animals. If you are doing counting, watching turtles, let's say, they move slowly, so you will be able to observe them. But if you are watching leopards, let's say, I mean, if you blink your eye, you might miss it. So, so what I'm trying to say is, of course, when you are dealing with the real situations, you have to see whether your assumptions are reasonable. Okay, so this is pretty much the same. I have a special ball out of the in a box with N balls, and I'm picking K balls out of it. And suppose this is the winner ball, and that you if you pick it, you will win. And so we are doing something we all know, because you have a K try, and here you assume after you pick the ball, you put it back in. So this would be K over N of picking up the special ball. But another way to approach it is in a combinatorial manner. N choose K denotes all the possible K balls that you can choose from this box. And then in order for the special ball to be chosen, you have to choose it. There is only one way. Either you just write 1 here, or you think of it as 1 choose 1. And you still have K minus 1 balls to choose from N minus 1 balls in the box. And so N minus 1 choose K minus 1. And if you simplify it, it works out to be a very simple number, K over N here. Okay, I think this is pretty easy. So computing probabilities. Okay. Now, what is this? A fair die is tossed. Oh, okay. Did it appear something weird in your lecture notes too? No. Okay, so probably, I don't know why. It's Jane. So let's look at this. A is the event of getting even numbers. So the experiment is I roll the die once, and the die is assumed to be fair, all right? And then B is I get either 1 or 3, and then C will be either 3 or 6. So we just list them out, and so these probabilities are just using equally likely probabilities. We are justified because the assumption is on the fair die here. All right. As A and B are mutually exclusive, okay, let's look at this. There is no common element between A and B. So if we are interested to compute the probability of A union B, then we are just using the axiom number 3 in the axiomatic probability approach. So that would be 1/2 plus 1/3, and this will give us 5/6. Of course, another way to do it, that is where the consistency is. You first form A union B, which will be 1, 2, 3, 4, 6. And so this event is now, I have 5 outcomes, and out of 6, so I have 5 over 6. So what I'm trying to relate to you is that the consistency. I could have found out the outcomes of A union B first, which is 1, 2, 3, 4, 6. And so as a result, I have 5 over 6. Whereas if I do it piece by piece, I will get 5 over 6. So this is exactly what the axiom 3 is requiring. In this example, it is trivial. You will accept it, do it. But the axiom number 3 is spelling it out, that either you find out A union B, what A union B is, and then calculate the probability there, or you do it piece by piece. It should give you the same answer. Okay, now we wanted to calculate A union C. Well, of course, if we have already spelled out the set, A union C would be quite easy. It's 2, 3, 4, 6. So I would have 4 elements. So I could have just calculate. This is 4 over 6 by really spelling out the outcomes. But I can do it in using the proposition, that is the inclusion-exclusion principle. I add individual set, the probabilities, but then I have double counted those that are common to them. So A intersect C will be just 6, all right? So either way, you have to do some set operations. So this is 1/2, and this is 1/3, and this is 1/6. So as a result, it's 4 over 6. Okay. So alternatively, we can do this, and so basically we are verifying the consistency. Okay, about Linda. This kind of example is coming from, I encountered this when I think one guy is called, well, I should have more respect for him, Professor Daniel Kahneman, an economics Nobel laureate, I think in 2004 or 2002. And his collaborator, Amos Tversky, or I think both of them should deserve the Nobel Prize. Actually, they collaborate a lot, and but Amos died quite young before the Nobel Prize is awarded. So in his book, actually the book should be is recommended reading. The book written by Daniel Kahneman is Thinking, Fast or Slow. So basically, in the book, he is describing two kinds of thinking. One is autopilot, fast thinking, and then the other is slow. In the book, he cited a number of these similar kind of biases that people might, if you are thinking too fast, you might make the mistake. So in the description here, Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Now, which of the following alternatives is more probable and why? Linda is a bank teller. Now, of course, we are putting in a lot of stigma in what the bank teller is. I mean, we have our fixed prototype of a bank teller. And then Linda is a bank teller and active in feminist movement. I think you can see your notes right away. We should have hide the notes, that slides. What do you think is more probable? So as it turns out, A is more probable because the B description gives you an event, and the event is a smaller event than the event described in A. All right. So bigger event, bigger probability. Okay. Now there is a tendency, especially when the description or describing certain situations, very often in a lot of, say, legal, say, the prosecutor or whatever, the prosecutors, I shouldn't use the word spin, try to argue, but in fact, he is reconstructing the story of the crime scene. He may not have the evidence, but he might have bits of evidence, but then he put them all up in a story. Now, and so he fill in the detail of the event, and people think that it's more probable because if he fill in the detail from evidence A lead to evidence B and so on. But in fact, unless the connection between evidence A and B are already verified, otherwise the connection is actually the prosecutor's impression. All right, so it actually makes it less probable. But for a lot of people, because he is able to transit from evidence A to evidence B in a smooth way, but the smooth way is actually in imagination, then it is less probable. All right, but it is more believable. Okay, so let A be the event that Linda is a bank teller, and B, that she is active in the feminist movement. So the statement small b is describing A intersect B, whereas the statement A is describing just A itself. So as a result, the event A is more probable than the other. Now the same book actually that I mentioned by Daniel Kahneman, Thinking, Fast and Slow, has other examples. For example, in a room where you know there are 70% of the people are engineer, and then 30% are lawyer, and so you wanted to just make a cold guess when you meet someone in the party, then what Kahneman say, or I mean we do here, you do not forget about the baseline probability, the baseline distribution, so and so on and so forth. The hall pageants. Audrey is taking part in her horse pageant. The probability that she will win the crown is 0.14. The probability that she will win Miss Photogenic is 0.3. The probability that she will win both is 0.11. Now, as a way of doing exercise, the best thing is to lay out the event in a nice way, and then we translate the descriptive story here in terms of your event. So, the next slide is actually translating it. So winning the crown is event A, and winning the Miss Photogenic is B. And what the story given us is that the probability that she will win both is 0.11, and that is the probability of A intersect B. So you are given probability of A, probability of B, and then probability of A intersect B. So now the question is, what is the probability that she wins at least one of the two? So you translate it in your notation. So what the question is asking is the probability of A union B. Okay, once you translate everything here, you already have three ingredients here. Then you are just applying the inclusion-exclusion principle to do so. So we are going through this. So we are given these three probabilities. So it's just a straightforward application of this, and this is 0.33. The probability required that she win one of them. All right. So remember that I think we have not spelled this out in a very clear way. So let me do so. Actually, in the course of proving bigger event, bigger probability, we have done something like this. If A is a subset of B, then the probability of A will be equal to probability of B minus the probability of B minus A. This is a set minus. And it is a slash, okay? It's not a vertical stroke. Why am I so fussy about whether it's a slash or vertical stroke? Because we reserve the vertical stroke for conditional probability. So for this reason, we have to be careful. So what is going on is this is the B, and this is the A. This middle part is according to the set notation, is B set minus A. So B is actually coming from B set minus A, the part outside, and this is a union and A here. Now, another common mistake among students at this level is they would instinctively use a plus here, all right? But this is not the notation we use for set operations. Plus is only for numbers, all right, unless you define it. And so because of the fact that the two pieces do not overlap, so you have this. And so as a result, by moving this term to the left, we get this, all right? So this is how we do this. A union B is an event that contains A intersect B, all right? So as a result, we will be just calculating the probability here minus the probability of the thing inside, all right? And so we have this. Now, of course, this is just one way of doing it. Another way is to do it piece by piece if you have the pictures. This is just quite formal using some numbers. But let me just draw it, and so that might be easier. So this is A here, and then this is B here. So the last sentence says that winning boat is 0.11. So this is 0.11. So you fill in things from inside out. All right, and then this is 0.14. So as a result, this is 0.03. All right, because the whole thing is 0.14. And here, that has to be 0.3, that would be 0.19. So after this, then for answer B would be 0.22. Answer A would be winning one of them would be 0.33, right? So it's just simple adding things up rather than applying the formula in a mechanical way. Okay. A poll of statisticians in United States was conducted to ascertain their professional responsibilities. An analysis of their responses gave the following description. We have ABC here, 3 descriptions. But the descriptions can overlap for some people, and 10% are involved in all 3. So basically, we have 3 events, ABC. Here, the story says that 10% belongs to all 3, and then they start to describe the pairwise, all right? And then using this information, we want to find the percentage of all statisticians in USA that are involved in B and C, all right? So we just apply the inclusion-exclusion principle, or you can start to fill in the sectors of the Venn diagram. That would be more visual. So we basically were given this. So this is from the survey, and you have this. Now you remember the probability of A union B union C involves how many terms? There should be 7 terms, right? Okay. 3 single event, and then 3 pairwise, and then I have 1 that belongs to all of them. So that would be my 7 terms on my right-hand side, and then I probability of A union B union C. So now they also give us another clue that the probability of all of them is equal to 1. So basically, you are given 7 numbers, and the equation 1 number is on the left-hand side, and then 7 numbers on the other side. So I have 8 things, and now basically you are told 7 things, and so you should be able to calculate the remaining guy. And so so we just put that in, and so it's just a little bit of calculator things. Okay, maybe we stop here and for a break. Not end this lecture here. Okay, your weekend hasn't come yet. Okay, so let's come back at 10:50. For those who haven't had registered any tutorial group, you can do so during the break. Okay, there are four classical probability problems. I mean, that has been around for a long time. And one is the birthday problem that is described here. And then another one would be a matching problem, I mean, usually they describe in a story. We'll describe it in full, but basically you are thinking of n gentlemen with n hats, and then when they entered the party, they leave their hat in a room, and then when they leave, they just randomly pick one hat. So the question is how many, on the average, of the variations of the number of people getting back the right hat. Now this is in hat and gentleman kind of scenario, but people also talk about envelopes and letters. Or another one is you shuffle a deck of cards, you arrange 1 up to 52 cards, and then you have another deck of cards, 1 up to 52, and then you look for the corresponding places whether there is a match. So it appears in different situations. The other two, I think one is called the voter problem. When you know, I mean 50% you vote for candidate A and 50% you vote for candidate B. But as you count the vote, sometimes we might have the illusion that one of the candidates is leading for a long time before it's being overtaken. Because at the end, it would be 50-50, all right? But at the stretch, there might be situations that people are thinking one of the candidates is winning by, likely to win. So there is this kind of problem that have been around. Here, this is the following. This is how you, well, here you say you want to add awesome afterwards. One way is that you can win a free lunch. I mean, especially people don't believe it. Because if you describe these situations, now basically let me describe the situation. You have n people and the n is not very big. In most cases, maybe 23, 25. And then what is the probability that among the people that you have in the party, they will have a common birthday? Now, this is a little bit not so graphic. Let me put it the other way around. You have 365 boxes. The first one, you name it box 1, and then the second one, you name it box 2. I mean, nothing's magic. And then the last one is 365. And n is the number of balls, okay, say 23. And then you start to randomly throw the balls into the 365 boxes. And you only have 23 balls, all right? So I asked, what is the probability that I will see at least one box with more than one balls? Now, most of the boxes are empty. And you might think that if you're randomly throwing the balls into the boxes, each box either has 0 balls or 1 ball, right? So as it turns out, you only need 23 balls or more to make sure you have more than 50% chance of having one box containing more than 1 ball. Now, this is a birthday problem. I'm not sure whether you are aware of this. If I don't gamble, okay, my disclaimer. Okay. Whether you believe it, you bet, right? So anyway, people observe some 4D patterns in the past. In Singapore, many people place what they call a 4D, buying a 4-digit number. And I think the Straits Times will release the result. I think you can place 4D 3 times a week, something like that. You either pay 50 cents or $1, and you can really tell I didn't even buy once. All right. And then there are some occasions that Straits Times say, oh, wow, there are occasions that the same number win the first prize or the third prize at the same time. Now, people are very surprised. And in fact, in 2006, one day when I was about to leave office, I get a phone call from a lady, and she was asking me something like the 4D things. Well, my first thing is, she did not explain who she is. Then I'm a bit skeptical, and especially it's a lady. Okay. Well, okay, I don't want to say more, otherwise I might be very famous or infamous. So anyway, so since she did not explain why she's asking this, and then she says something like the birthday problem and 4D things, I just don't want to entertain the phone call. Then the next morning, my colleague, a more senior colleague, told me he referred me to a lady from Straits Times and asking about the occurrence of the 4D. She saw that one 4D number wins the second prize and the third prize. I think it's in 2006, October something. Then, and then my colleagues say I try to solve it as a birthday problem. And I mean, it's totally out of reach for the journalist. And then she wants a second opinion. Then my colleague asked her to call me. But anyway, I saw the Straits Times claim is 1 in 100 million chance of having. So basically what she was thinking is, for 4D, you can buy 0000 up to 9999, right? So you think of it now as 10,000 balls, right? And for 4D, they pick 3 for the prize 1, prize 2, prize 3. And then there are 10 others for whatever they call consolation prize. And then another is another 10 for some even smaller prize. So you are just imagining you are throwing 23 balls into 10,000 boxes, basically. So it is really the birthday problem in that formula. All right? And the Straits Times calculations, since she didn't believe us, she say it is 1 in 100 million. How does she get 1 in 100 million? Of course, my guess is you multiply 10,000 by 10,000, that would be 100 million. Okay? So this would be a different birthday problem. All right, I will tell you. All right, so we cast this into a birthday problem. Now, this is a very interesting problem because it illustrates that I have told you sometime when you want to calculate the probability of the event, you want to calculate the probability of the event head-on. Or another way is to calculate the opposite of the event. And this is the situation here. It is much simpler to describe the case when the event is the opposite. All right? Now, having a common birthday, the opposite is that all of the n people have different birthday. This is much easier to describe than having a common birthday, because you might have cases that only 2 of them share the same birthday, and then everyone else have different birthday. But then you might also have 2 pairs of them, they share the same birthday, but the 2 birthdays are different, or 3 people having the same birthday. So you have so many situations that you have to account for. And some of the situations might overlap with the others. Because let's say you want A, B, C share the same birthday. So you might have A, B share the same birthday and B, C share the same birthday. So as a result, A, B, C will share the same birthday. So there are this kind of overlap happening. Now, as it turns out, it is much easier to calculate the opposite. Okay, so we assume each day is equally likely to be a birthday of everyone, and there is no leap year. Now, if you want to account the leap year, we just change 365 to 366. So it's not a big deal. And assuming equally likely to be the birthday, this is not true. All right. If you look at Wikipedia, I think there was some time ago I checked, and certain months are more popular for birth. All right. Something like October or something. It might have to do with the after effect of Chinese New Year or New Year, that kind of thing. Ask your parents, right? So now if the days are not equally likely, the probability is even higher. So what we are calculating, the probability here, is the most conservative probability, meaning that if you have a certain favorite day for birth, then the likelihood of getting a pair of people sharing the same birthday will be higher. So if you're betting on having a common birthday, you are in better shape. All right. So what we are calculating is the most conservative probability. And let AN be the number of events that at least 2 people among the N people sharing the same birthday. Now the first thing is I want to calculate the total number of outcomes among the N people. So each one has 365 days to choose from. So I have 365 to the power N. So you think of it as an order pair of N entries, the vector. The first entry of the vector is the birthday of the first one, and so on and so forth. So you are keeping track of the numbers. And so we are asking how many such vectors is possible. And each entry, you have 365 choice, and you have N steps. So, so it's 365 to the power N. Now, it is much easier to work out the opposite, AN complement, because we can argue in the following way. So we ask the people come to choose their birthday. I mean, this just imagine, all right? They can't choose, all right? But the first guy, having no restriction, so he will have 365 days for him to choose. So he will have 365 ways of doing it. Now the second guy come in order to be exactly opposite. That means his birthday has to be different from the first guy. The first guy has already chosen his, so and he has chosen 1. So there are only remaining 364 days for him to choose. All right, and the third guy, the first 2 guys have chosen 2 different days. This is crucial because their birthdays they don't share the birthday. So they have chosen exactly 2 days, and so there are 363 days left for the third guy. And then the very last guy, the nth guy, N-1 people before him has chosen their own birthday. And since they are all different, so N-1 day have been exhausted. But so the remaining choice would be 365 minus the number of days that have been chosen. That is N-1. So I have this. And then I can rewrite this in this form. The first term disappears because the first term is 365 over 365. So basically it's this. We can calculate this probability very easily in a recursive manner. All right, either you write a little script, or you can even do it in Excel, that you can do it for any N. And so I can calculate the original probability. The original probability is 1 minus the probability of the opposite, okay, and which is this. So as a result, we can calculate this in a neat way. So 23 is really the threshold. Pn is equal to 0.5073. And so if you have a room of 23 people, especially you know that there are no twins there, all right? Otherwise, you definitely win. And unless one twin is born before 12 midnight and then the other is, I mean, that is really unlikely. So you have a 50.7% chance of winning, okay? And the probability goes up to 1 very quickly, or the other one is the opposite, goes to 0 very quickly. The reason is you are multiplying the numbers smaller and smaller. All right, so that is why it goes to 0 very quickly. It's faster than the exponential. All right, so here. So in a class of like 30 people, it is 70%. And if I have 50 people, it's almost like 98%. So I think this is a hard calculation. The question is how can I have an intuitive way of explaining it, all right? Okay, one way you can think of it is the situations, because we fail to think of some situations. Okay. Maybe I'll just do some simulations. Now this is the approach here is I'm based on equally likely approach, meaning that each day is equally likely to be someone's birthday. So if you do not know how to calculate this, you can do simulations. It is a very short code, but let me try to do a little bit more. One way to simulate this is that you think of putting the numbers into a hat. So 1:365 means I'm putting ticket 1, ticket 2, up to ticket 365 into a big hat, all right? And then I'm going to pick 23 tickets. What I'm going to do is I pick ticket 1 at a time. Okay, I pick the first ticket, but I put the ticket back into the hat first, and then shake it, and then pick the second one. So here I have to tell R that I'm selecting things with replacement. This is what we call sampling with replacement. All right. If you write false, means that once the number is being taken, you will not take it again. So this is sampling without replacement. So I can do that, and so you have a bunch of here. So it's a test of your eyesight. Do you see any common birthday here? I think you guys are much better. Okay, now if I do it again, this is another illustration. It would be another different set of numbers. Is there any common birthday? No. Okay, now if I sample it, we anticipate it take a little effort to spot them. So one way is to see whether I order them. Okay, are there any common birthday here? Okay, yes, no, no, right? Okay, now this is still a little bit troublesome. So sorting, I still have to eyeball it. Maybe another way is I form a table. Basically, I count how many times a particular calendar day has someone's birthday. So now, because I didn't save my answer earlier, this would be another round of sampling. So the result would be different. So I will have this. Sorry? Oh, yeah. Okay, then. I don't know how to fix this. Anyway, let me redo it. Yeah. Okay. So again, in these situations, there is no. Okay. Now, it's like flipping the coin. I've done it 3 times, and they are all tails. And so to cheat a little bit, I increase the number. All right. So I have 50 of them. So so you will see. So 2 people are born on the 82nd day, so you can change it to the calendar day. And you will see quite a complex situations. There are quite a number of 2s. In fact, it is very rare to have 3, all right? So having 3 people sharing the same birthday is very... Now, this is a better way of doing it. I told you I'm not a computer person. So so this code is actually someone written it online, so I copy it. shamelessly. All right. The first thing is that the guy who wrote this defined it as a function. Instead of every time when so let me break it down. So the first thing is that he sampled the 365 days for n people and the sampling with replacement. And so it returns back to a vector or a list. Actually, I'll think of it as a list. So a list of the birthdays. And now there is a command called duplicated. So as you go along the member of the list, you check whether you have seen it before. So the first one will be false because you are the first guy. The second guy, if it's not the same as the first guy, it will also be false. So if you do it line by line, it will return a string of false, 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 true, and so on. And then I just want one single return, any, means that as long as there is one true, I will return it, all right? Okay, so you can do it one round. For example, same birthday. And then now I can vary so let me go back to 23 people. So in these situations, yeah, I have what I want. Okay, otherwise I'm very embarrassed. For this particular group of 23 people, I have some common birthday. But I do not know whether there are actually only two or there are two pairs or very complicated situations. Okay, the nice things that I keep advertising because you guys are in this business. So I'm going to repeat it 10,000 times. It shouldn't take long, otherwise I don't need to teach. So it is 0.9724. Now this is for, I'm sorry, I'm doing it for 50. So let me, okay. So I'm repeating it and then for 50. Let's check our answer. Our actual answer is something like, so it is pretty close, right? How do I? So it's 9724. You don't have any more decimal places because it is a 10,000 here. And this number is 979. So it is off a little bit, all right? If I were to repeat it, I would have a slightly different answer. Okay, so now I have only 96, 91. So this is my point. If you do simulations, you know roughly that your answer is right, but it is not exact, all right? How exact it is, that would be another matter, all right? So what I illustrated is two approaches to calculate the same problem. One is the frequency approach, which is done here. So I do it 10,000 times for parties of 50 people. And another one would be just by the principle of counting. Okay, so now this is usually confused with the other one. Maybe before I do so, let me explain why the probability can be so large, even for 23 people. The first thing is that I do not specify which pair of people that they can share. So, so I let A12 is the event that people 1 and people 2 share the same birthday. Okay, and similarly, Aij, I is less than J, and let's say I'm considering only 23 people. And how many pairs are there? So again, this is our counting things. 23 people, we choose 2. So it is 23 times 22 over 2. So it's 253. So that is why, so you will actually have 253 pairs. And so because of this possibility, now for one of them, say let's say 1, 2, it doesn't really matter because I call I as 1 or 2, J as 2 because it's just a matter of labeling the people. So the probability of having 2 people sharing the same birthday is the first guy has 365 days to choose from. The second guy has to choose the same day that the first guy chosen. So, and this is 1 over 365. And now if you really want to do the calculations, so this is what the probability is. And there are 253 of them. Okay, and each one is about this. But then, of course, you have to take away the intersections. They overlap because if 1 and 2 share the same birthday, 2 and 3 share the same birthday, then 1 and 3 will also share the same birthday. So you have calculated this more than once. But you will see that the probability is due to the fact that there are many pairs here. It is because we haven't specified Ku and Ku share the same birthday, and then there are so many of them. Now, if you look at this situation, then you will not be surprised. Okay. Now here. Okay. I don't know whether this is called inverse birthday problem, but this will be the birthday problem many people have in mind. How large does a group of people have to be such that the probability some of you share my birthday? That would be something different. And the probability would be, if I pick you, you have 1 over 365 to have my birthday, right? To share the birthday. And then every one of you will have 1 over 365. So if it's n people to have a common birthday, the probability of having one of you among the n to have a birthday as mine, then it will be 1 over 365 to the power n. Okay. That is the, okay, everyone has the same birthday here. Okay, maybe I'll do it. All right. Okay, so this is me and n of you. So the probability that I want to calculate the opposite because there might be one of you have the same birthday as mine, or 0 of you, 2 of you, right? So I calculate the opposite. None of you have the same birthday as mine. So for the first person, the probability is 1 over 365 to have my probability to share my birthday, and this will be not having my birthday. All right, so this is person 1. And so you do it for this. And then this is the n guy. And of course, this is, I have to 1 minus, because this is the opposite. All right, so this is the probability that I would be looking at, Pn tutor. And so this would be quite easy to solve because it is 364 over 365 to the power n. And I wanted to find out what n is in order the probability is bigger than half. So, so you can do the calculations. And n now has to be pretty big in order to do the trick. So we can solve this. So I told you you can take R as a calculator. So n roughly equal to log 364 divided by 365, and then divided by log 2. All right. Now in R, I think if you just put log, I don't remember now. Either they would use base 10 or base E. So you have to tell them what is the base that you're using. But it doesn't really matter because I'm taking the ratio of 2 log. So as a result, the base is immaterial. Okay. Why is it refusing? Okay, so I think they don't understand this. Okay, if you don't like it, say let's say I've used base 10. Okay. Maybe I change it to small l. One of the annoying thing about R is you have to know, I don't know why, but I think you can use your calculator. I'm sorry about that. Okay. But the number of n is reasonably big. So it is because you have specified the date. Okay. Oh yeah, it's done here. I am stupid. All right. So we need to ask 252.7. This is very close to our 253 pairs, right? Just now, 23 people, and then you have 253 pairs. So that is not totally surprising. All right. And I think it is even a little bit more surprising is it is not about half of the calendar days. Half of the calendar days is 182. So when you throw the ball at random and you specify which box that is your box, that you have more than one ball, at least one ball to fall in, it turns out you have to try about 70 times more than the half of the boxes. All right, you may not even fall into it. Okay, so we mentioned it, and then now the conditional probability. Let me see. Okay, let me introduce the definition first. The probabilities assigned to various events depend on what is known about the experimental situations when the assignment is made. What happens if we get subsequently some additional information? How do we capitalize this? For example, how does the information that an event A has occurred affects the probability assigned to the event B? So let's have two scenarios. One is you are interested in computing the probability of B. Okay. Another situation is you have some extra information. You know A has already occurred. Okay. Now, for example, this is helpful. If the two events A and B are mutually exclusive, an example is you are in the lecture theater, and then the other event is you are not in the lecture theater. So if I want to calculate the probability that you are attending this lecture, that it would be something. But if I know that you are not in the lecture theater, then the probability that you are attending my lecture would be 0. So the probability of attending the lecture change as the information is given to you. Okay, so this is the definition. For any two events, A and B, we will come back to this requirement in a minute. The conditional probability B given A has occurred is simply defined to be the ratio of A intercept B over probability of A. Now this is the definition, and this stroke is a vertical stroke. So that is why I was saying don't have a slash here, because it might be read in another manner. Okay, so this is the definition. And now I go back here. The probability of A is positive. It's just to avoid the embarrassing moment that I have a 0 here. All right, but it's not going to be a big problem. Sometime if you're willing to, because the top part would be if probability of A is 0. What is the probability of A intercept B? It has to be 0, because A-intercept B is a smaller event than A, then the probability of A is 0, then probability of A-intercept B has to be less than or equal to 0. But we know that all the probability has to be non-negative, so there is no way out, and it has to be 0. So you will be in a situation of 0 over 0. Now, this would be not meaningful in these situations, but it would be meaningful still later on, all right? So let's calculate the situations. A fair die is rolled twice. What is the probability that the sum of the two rolls is even, given that the first roll is a 5? Given that it's two questions here. All right, so let's deal with A first. A is just in itself. So let B be the event that the sum of the two rows is even, and A, the event that the first row is a 5. So we list out the sample space, and B to be even. So we just pick up the right thing. Actually, you don't even need to list in order to calculate B, because when you add up two numbers, integers, it would be either odd or even. And since you are exhausting it from in a very systematic manner, 1 to 6, and another one is 1 to 6, so it would be half and half. All right, and then A. What is the probability of A? Probability of A is that now my first row is a 5. So the advantage of listing it is to illustrate the situations. I pick up the sum is equal to is even. So I will basically you can highlight those that will give you even. Say for example 1 1, 1 3, 1 5, 2 2, and so on. But now you are given the information the first row is 5. So you will restrict your sample space now to just this row instead of this array of numbers, because you know you get a 5 there. And this is why the sample space is smaller. So I have 5 1, 5 2, 5 3, 5 5, 5 4, 5 5, and 5 6. And so we are interested to look for instances among this row that gives us an even sum. So this one, and this one. So basically, you want the second row to have had an odd number as well, because your first one is a 5. So 3 instances out of 6. So that would be 1/2 here. Okay, and so right. Okay, so we get this. I want to change the order of presentation a little bit so that I will just have 1 minute to cover this. All right. So I think it is somewhere down in the lecture notes, but I think it would be a pity not to say it. Okay. So the definition of the conditional probability. Is given by this. Okay, so what I do is I multiply this over. Okay, and I write it this way. Okay, and now the advantage is that first, this is what we call the multiplication rule. Meaning that if you want to calculate the probability of a joint occurrence of two events, you can do it in a sequential manner. Now, the left-hand side has nothing to do whether you're doing it sequentially or not, but you are doing it jointly. But the right-hand side, I can have this interpretation. I first insist that the event A has to happen, all right, because I'm interested in the probability that A and B happen. So I insist that A happened first, and after which, given that A has already happened, the probability that B will also happen. So this is, I'm doing it in sequence. So I think of A happen, A does not happen. But then here I will have a B and a B. And I'm interested in this branch only. We will, because the representation here is quite useful, later on we will think of it as a decision tree, probability tree to do the calculations. This has something to do with the Bayes theorem later on. Now coming back here, we can avoid the embarrassing situations. Here probability of A can be 0 because the probability here, you guys have already answered that this probability has to be 0. And so this is 0, this is 0. So you can define this probability in any arbitrary manner. All right. So there is this, I mean, it's really up to you how to define it when you, the probability of A. We can't define it in this manner, but because you might run into 0 over 0, but we will not have these situations here. Now there is another parallel answer way of doing this. The probability of A intercept B, because now I imagine B happens first, and then given B happens, I want A happen. All right. So so this I have two choices of writing the probability of a joint occurrence of the two events, and depending on which one is more convenient, then we will go by one of them. Okay. I'm quite sure the lecture notes will sooner or later will cover this, but I think it would be better to mention it here. Okay, so maybe I'll stop here. So I'll see you next week.
I need to ask you regarding the birthday plot.
Yes.
Okay, so just like an example, right? I understand, say, we have, for let's say you choose when you choose a person, we 365 about n how many people depending on how many people we have right now. Is this right? 365 to about n plus 365. But then I don't understand why it's like 365 and 364.
Oh.
But I don't really get that.
Oh, okay. Because I'm considering the situation. I'm interested in calculating the complement.
Okay.
And
so
then
this is the complement.
right,
Yeah.
and I wanted to the complement over the sample space, right?
Correct.
So here you get it. There are 365, right? And AN. So I'm thinking of person 1.
Mm-hmm.
So out of the calendar day, you can choose one out of 365.
Oh, okay.
Right?
Mm-hmm.
And then out of the day that you have chosen, the person 2, suppose this is 10, then the person 2 can choose 1 up to 9, but then he cannot choose 10.
Choose like for how you say person that doesn't have the same birthday. Is it?
Right, because I'm looking at the opposite.
Correct.
Yeah. So he would have 364 choices. Does it make sense now?
Oh, so basically we are removing the person who had with the specific birthday. So now we have 364 choices of people. We don't have this birthday, and then 363, 362,
Yeah,
and so on.
Because I basically want all of them to have a different birthday, and I let them choose in a sequential manner.
Okay.
So the first guy had chosen, then you hide that particular day from his choice, right? So he has only 364 choices. Then the second guy choose one day, and then you also hide it for the third guy. So by doing this, everyone will have a different birthday.
Oh, okay. So in that case, then it's up to the n number of people where we are basically done. Then we've hidden the birthday such that we won't have a repeat birthday.
Right. We just don't want to have a repeat. So the end guy, the last guy, he N minus 1
sit
days
into all
have
the
already
lectures,
been
but I don't
chosen
take
because
the final.
everyone in front of
So I don't
him
get a grade.
choose a different day.
Okay.
It shows
So
up on my
this
transcript.
N minus 1 day has to hide from him.
Yeah.
And so
Is that
365
an
minus
option for any website?
whatever is hidden from him.
Oh,
Was it just for-
okay. Then we can just, this is just an alternative way of representation compared to this.
Yeah.
Then, my second question is regarding the log 0.5. I don't really get how we use log. How you get the log here.
Oh, because I was solving this,
Correct.
Oh, so if you only got like
1 minus 3. Because,
C minus,
okay.
you can
so this is this. So it is something like,
oh, that's satisfactory either way. That's nice.
I wanted to solve the n, so I take log.
Oh, because that's
True.
yeah. That's the way.
Then, yeah.
Now remember this is not negative. So when I divide it, the inequality is reversed.
Correct.
All I did was to pass, and I couldn't do that.
Not even that.
And we put
That's
out
not
to be
real.
about 250 something.
So how many modules are you in?
I will take a picture now.
Oh, okay.
Oh, you can have it.
Just in case people don't see me.
All right. Okay.
Thank you so much.
Sure.
Yes, Professor. I had a question. I was going through the
Yeah,
tutorial.
yeah,
In
right.
question 6,
Right. The red
I
riding
don't
hood
really
thing.
understand.
Oh, the first.
Like even the first one, because the
Oh.
first one I did a permutation
Right.
of indistinct groups,
Right.
and I got this answer. But then the solutions have a combinatorial.
Oh, this is the you can write as a combination because if it's C21 choose 8 is also this number.
Yeah, I noticed they're the same number, but I didn't know
Oh,
why.
it depends on the way you think.
Okay.
All right. So
Yeah, I was like, I couldn't figure out how to
from
think about it.
from A to B, right?
Yeah.
This is 0, 0, and then this is 13, 8.
13, yeah.
So that means Red Riding Hood has to go use 13 east step, going
to
to
what?
east, going east. I
Yeah,
mean east step,
13 east steps.
and then and also 8, 9 steps, right?
Yeah.
Okay, so a path is actually consists of a string of this E and N.
Okay.
It's just like spelling the word. Okay, I have a word which has
okay.
13, and so this is your arg. So if I imagine
So
it's
that's
just like the
I'm
mix,
ordering it,
right?
yeah.
So you have 21 factorial,
Uh-huh.
and then but they are similar, they are identical. So you have to do it this way.
Okay.
Yeah.
Yeah.
Or another way I'm thinking of
Uh-huh.
is you have 21 slots, right,
Yeah.
in my path,
Uh-huh.
and I pick 8 of them.
Oh, sorry.
I pick 8 of them for me to fill in the end,
Uh-huh.
right? I pick 21 positions, 8 positions out of these 21 positions for me to fill in the north.
Oh, so you're choosing a group of 8 from that 21.
Right.
And you assume that everything you don't choose is then the E.
Yeah,
'cause it
yeah,
has to be.
right.
Oh,
And so
okay.
this
That
is a
makes sense
different
how you
way.
get that.
So it's different way of seeing the whole thing. I mean, one is
Yeah.
I think of it as a word and then rearranging all the different.
And
words.
that's where an order would count
Right.
in that instance.
Right.
But here,
yeah.
you're already taking
You
order
you
into
you are
account.
you are thinking of giving people's instruction.
Yeah.
So you leave this instruction 13E and then so the guy has to, right?
Yeah.
This-
Mhm.
But if you alternate it, then it might be like this, right?
Okay.
So each different word that you form is an instruction
Different
how
way
the
to
path
get there.
is.
Okay.
Yeah.
And in this way, that makes sense. Because
Yeah.
in this way, you're still being
Yeah.
distinct. But then how would you, like, if you want to avoid 10-6?
Oh, okay. One way is A.
I assume it would be like an
Okay.
opposite?
So if you from A you go she go to her grandma consists of 2 different kinds of path.
Uh-huh.
One path is she actually meets the big bad wolf.
Yeah.
The other one would
doesn't.
be she doesn't, right? I mean, so, right?
Yeah.
So it might be easier to calculate the path in this way
Yeah. The path.
because you can think of going through this path consists of 2 steps.
Uh-huh.
One step is from where Red Riding Hood lives to go see the big bad wolf,
Uh-huh.
and then from the big bad wolf, so you count how many ways Red Riding Hood. So it's the same problem now.
I see. Okay.
And then
So, you're seeing how many ways?
yeah, so
that
it's
makes
it's
sense.
part A, but part A now
How many
we
ways
pick the
you
part
get
A
there
two
and then
times.
to part B?
Yeah.
Okay.
And then but you have the answer in part A here.
yeah.
So whatever left here you must.
And you want the
yeah.
opposite. Oh,
Or
okay.
something like
That makes much more
And then
sense.
part C is similar.
Thank you. Yeah, I just saw the combinatorial and like the solutions, and I didn't know why you would.
Or
do-
it's just the answer. The solution will be.
Yeah,
worked
yeah,
out.
it's not.
Yeah, but it's good to keep this in a picture form.
Yeah. Awesome. Thank you.
Okay.
Professor, I just wanted to check if it's possible to change my tutorial slot to one of the 4 units.
Sure. Yes,
I'm originally in tutorial 3,
okay.
but since you mentioned it's like overcrowded,
Yeah. So
I would love to change it to okay.
Can I know when will this be done?
it is you just don't worry. I mean, you just go there because you sign up on Monday.
No, actually I have another class,
Okay.
another module that clashes with my sister.
The one that you chosen.
So
You can choose. You can change it now. Do I get you right?
No, because the other
Okay. Let's
person
look
is
at here, right?
trying to allocate the module to me.
Okay. Okay. Anyway, so this is you, right?
Yeah.
So you always you leave group 9
Yeah.
and then you want to go to group 11.
Yeah,
But now this is not good for you, right?
Sorry.
What do you want to choose?
Oh no, because this clashes with another module.
Right.
Then the person trying to allocate the module to me cannot allocate because it clashes with mine. So I'm trying to ask when will I officially change to the other
Oh,
group?
it is official. Yeah.
In the system?
Okay, the system will only appear much later because it has to be manually entered. So, but now I have the record that you are going there. So you on Monday you just go to the 1 to 2, and then we will take your name out from group 9. But this will happen maybe a few weeks later. But don't worry, I mean, as long as I have the information. So is that what you want to ask?
No, because the person needs to I need to officially change to another group in the system for the person to allocate
Oh,
the
so
module to me.
so you need to officially withdraw from this, right? Okay, you can't withdraw from your side. I because I don't do this,
I
so
don't think so.
okay. I have your name here, so I'll see if I can. Can't get to my. I want to save it to my thumb drive. Okay, my answer is, I mean, don't worry. You can go and try to withdraw it if you can. If not, then I'll ask my secretary to withdraw you from there. So what you can do is you tell your instructor over that call that you can join the other one. So yeah. So it's just